three button. Oh, there, that's better. Hi. Good evening, and welcome to Crossroads of Ideas, Leaping Forward, How Wisconsin is Shaping the Future of Materials Science. I'm Shelly Grandell. I am the Assistant Director of Education and Outreach at the Materials Research Science and Engineering Center here at UW-Madison. The MRSEC brings together teams of researchers from a variety of disciplinary backgrounds to tackle grand challenges in the materials science. The center integrates the discovery of new knowledge with creation of research-inspired educational materials, innovative programs that broaden participation in STEM fields, industry outreach to promote economic advancement, and professional development opportunities that train next-generation workforce. Today's event marks 2024's first installment of the Crossroads of Ideas program series. Crossroads of Ideas is a collaboration between the Wisconsin Institute for Discovery's Illuminating Discovery Hub, UW-Madison, and the Morgridge Institute for Research, and is an opportunity to foster dialogue between the community and local scientists. The series addresses issues that impact us all and highlights important research happening in our state. Since 2014, Crossroads has been a staple of public programming offered at the Discovery Building on UW-Madison's campus. Before I say more about this evening's event, we will take a moment to acknowledge the land that we occupy here at the Discovery Building. The University of Wisconsin-Madison occupies ancestral Ho-Chunk land, a place their nation has called Dejop since time immemorial. In an 1832 treaty, the Ho-Chunk were forced to cede this territory. Decades of ethnic cleansing followed when both the federal and state governments tried repeatedly, but unsuccessfully, to forcibly remove the Ho-Chunk from Wisconsin. The history of colonization informs our shared future of collaboration and innovation. Today, UW-Madison and all of today's presenting organizations respect the inherent sovereignty of the Ho-Chunk Nation and the 11 other First Nations of Wisconsin. The mission to empower diverse communities by promoting access to cutting-edge research is at the core of today's event. With today being Leap Day, we could not possibly have found a more fitting technology to explore than the local electrode atom probe, or LEAP. LEAP is a novel analysis technique combining 3D imaging and precise atomic scale chemical composition measurements. To help guide us through this topic, we are thrilled to have Dr. Katherine Rice with us today. Dr. Katherine Rice is the Applications Lab Manager at CAMECA Instruments in Madison, Wisconsin. Prior to leading the lab, she was an applications scientist at CAMECA for atom probe tomography. She received her Master's of Science and PhD in Chemical and Biological Engineering from the University of Colorado Boulder under the supervision of Dr. Mark Stojkovic and Dr. Aaron Saunders. Katherine completed a postdoctoral fellowship at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, before joining CAMECA in 2014. She obtained her MBA from the University of Wisconsin-Whitewater in 2018, and her research interests include atom probe tomography, microscopy, and materials science. So please join me in welcoming Dr. Rice.
That was quite the intro, so thank you, Shelly. So I'm Katherine Rice, Applications Lab Manager, as Shelly so graciously introduced me, and I'd like to talk about how the University of Wisconsin really played a critical role in solving some of the most important material science problems of our day. And so it's a really special day, comes around once every 4 years, so I thought it'd be a good time to review some of the famous leaps in Wisconsin. So don't try this at home, but we have the Leap of Faith in the Wisconsin Dells, probably the most famous leap of all from Leroy Butler, the Lambeau Leap. Up in Door County, we've got Lover's Leap, and a leap that is near and dear to my heart is the local electrode atom probe, which we make right here in Fitchburg. So I know everybody feels most comfortable when class starts with a pop quiz, so let's start there. So my question to you is, what is an atom probe? Perhaps it's a very big microscope. I think we can see that might be the case. Maybe it's a three-dimensional imaging technique. Perhaps we can detect individual atoms. Maybe it's made right here in Dane County. And anytime I don't know the answer, I always select E, which is all of the above. And I'm hoping to show you in the next few slides that that is indeed the case. So how does an atom probe work? Well, we start with a very sharp and very small needle-shaped specimen. So the end radius of this is somewhere between 50 and 100 nanometers. We can then apply a voltage to this specimen so that the ions are almost but not quite ready to evaporate from the surface. We can then hit that sample with a little bit of extra energy in the form of a voltage or laser pulse, such that the atoms evaporate essentially one at a time. Now, if you've taken chemistry in the past, you'll know that every atom weighs a different amount. Your carbon is going to weigh a different amount from your gold, etc. So by measuring the time it takes for those atoms to leave the sample tip and reach the detector, we have a time of flight, which is going to give us a mass, so we can identify that atom. And from where it hits on that position-sensitive detector, we can essentially back-calculate where it came from on the initial sample surface. So when all is said and done, we can create a 3D reconstruction of up to 80% of the ions in our specimen. Now, once we have that 3D reconstruction, the possibilities are really endless. We can cut this up in any kind of way we want to, which I think we'll see here in the next few slides. So what kinds of things can we analyze with the atom probe? We can look at things like entire semiconductor devices, so transistors, to see if any of those atoms are out of place. We can look at a lot of metallurgical applications, like clustering in steel, to see why it's strong or weak. We can look at things like geological materials, ceramics, and oxides. So as a general rule of thumb, because we're evaporating things one at a time, if it's non-porous and a little bit conductive at least, there's a good chance we can analyze it. Where we don't have a lot of applications right now is for biological materials. These are generally don't hold together very well under field evaporation. So anytime you say you make microscopes, people think, okay, you're curing cancer. Well, maybe not yet. Methods are being developed in that area, but that's not one of our primary applications. So I think it's worth it to look at really the small volumes that we're able to analyze with the atom probe. Now, on our x-axis, we have a lateral resolution. So we can kind of think of that as size of our data set. And on both of our y-axes, left and right, we have the concentration. So what concentrations of things can you detect? So a typical data set size is somewhere around 100 nanometers. And that's about 1,000 times smaller than a human hair, and maybe something like 100 times smaller than a red blood cell. So with our data set size of somewhere between 1 and 100 million atoms, if you're looking at concentrations of 1 part per million, you're going to need at least 1 million atoms. So sometimes we're limited in concentration by the fact that we just don't have enough atoms to analyze. So it's important to know that this is a truly 3D technique. And one of the great things about atom probe is it's equally sensitive to all elements in the periodic table. So we can analyze light things like helium and hydrogen just as easily as heavy things like platinum or gold, etc. But it is a destructive technique, so you're not going to have that original sample because the process is evaporating it all away. Now, although we're looking at incredibly small volumes, there are a lot of really important material science problems that can be solved by the atom probe. So probably the first question I get is, how do we make our sample in this tiny needle shape? Now, I know the term FIB has some negative connotations here in Wisconsin, but it also stands for Focused Ion Beam, FIB. Now, this is essentially an electron microscope with an ion beam attached. And what we can do is use that ion beam much like a sandblaster. So we can put a little strip of metal over the thing that we want to analyze, and then use that ion beam like a sandblaster to cut away material on 3 sides of that. We can then lift out a little bar of that from the surface and mount that multiple samples to the substrate posts, much like cutting up a Toblerone candy. And then we can use that ion beam like a pencil sharpener to kind of whittle away these chunks so we get our sample in the shape of a needle. And we can do that with pretty much anything you can think of as long as it can fit inside this electron microscope. So the basic unit of data that we're getting from the atom probe is a mass spectrum, which looks like this series of peaks. So what we do is go through this series of peaks, and every element has a unique isotopic signature. So we go through and we match that pattern of peaks to the theoretical distribution for the isotopes, and that will allow us to identify what that atom is. So we can then color these peaks and apply those assignments to our 3D position data so that we get our reconstruction. So our mass data plus our position data is going to give us that 3D reconstruction. So what kinds of things can we do with a 3D reconstruction? Well, we can take a small slice, so we have a 2D image that matches a picture. We can then break out the distribution of every element individually. So in this example, we have one phase that's rich in tantalum, aluminum, and titanium, and a corresponding phase that's rich in chrome, iron, cobalt, and molybdenum. We can also take our 3D reconstruction and define regions or surfaces. So in this case, we've created a surface of a particular concentration. Now what that means is that on one side of the surface, we have a concentration greater than 10% aluminum, and on one side, our data set is less. We can pick out individual particles that are fully enclosed by this concentration definition. We can look at individual atoms within that surface. Of course, we can get a mass spectrum from that area isolated from the rest of the data set. And that can give us a composition of a particle separately from the rest of the data set. So now that we've gone through how it works and how we might treat some of the atom probe data, I think it's worth it to look at how all of this got started. So hopefully you can accompany me on a little bit of a mystery tour from the 1960s up until today, where this was firmly a lab technology and is currently commercially available, easy to use, and a thriving company. Now, of course, this didn't come out without challenges that engineering had to solve, but the University of Wisconsin played a critical role in getting there. So the story really begins a little bit before the 60s, actually, in the mid-1950s with Professor Erwin Mueller at Penn State University. And he was working on a technique called field ion microscopy, or FIM. Now this is related to atom probe, or similar, in the sense that what you can do is take a sharp needle-shaped sample, apply a voltage to it, and essentially image the pattern of gas on that crystalline metal surface. So what you can see is this beautiful image that we have here in the kind of center of that slide, and that really describes the pattern of atoms on a crystalline surface. Now, one thing that kind of blew my mind when I was researching this for this talk was that the atomic nature of atoms was pretty well accepted in the 1950s, but there was really no direct evidence of that until field ion microscopy came along. So I just thought that that would be settled way before the 1950s, but that's what FIM did for this technology. So about a decade later, Professor Mueller and his student John Panitz basically are experimenting with this technique and found that if you turn up the voltage on this tip, you can eventually not evaporate the gas to kind of image that. You can evaporate individual atoms. And this was really the first one-dimensional atom probe in 1967. So the time of flight aspect was added a few years later in the early 70s, but throughout the 70s, 80s, and 90s, folks are really building these machines in their own lab to work on material science problems. So there are several groups around the world, Oxford University, a group in Japan called NIMS, and a group in France called GBM, which were leaders in the field. So our history takes a turn here to Wisconsin with material science professor Dr. Tom Kelly. And he really believed that the atom probe could be more than it was. Now, the machines people were building in their labs were slow and limited in some ways. So Dr. Kelly goes to a meeting of the International Field Emission Society and presents this idea that the atom probe could be a lot faster, could have a wider field of view to see more atoms. And unfortunately, people thought he was literally insane. And he was really ridiculed as the Jules Verne because people believed that these ideas were science fiction. But over the next few years, just a short walk away from where we are tonight, Dr. Kelly and his student, Dr. David Larson, or not yet doctor, began working on some of this fundamental technology to enable these ideas. Now, they were funded by the Applied Superconductivity Program right here at the University of Wisconsin and used some donated equipment to bring these ideas kind of to life. So I think what Tom Kelly did was really interesting and really important. He really brought together a crossroads of ideas. And that is forging academic lab technology which could solve these problems together with business-minded ideas in how to commercialize this and how to solve problems that were relevant to industry. So in 1998, this led to the founding of Imago Scientific Instruments and commercialization of the Local Electrode Atom Probe, or the LEAP. Now, sometimes good things have to come to an end. So Imago had a good run with maybe 10, 15 LEAPs sold, but was eventually acquired by AMETEK, which is a large American conglomerate, in 2010, April Fool's Day, another special day, and that is who we are today. Now, AMETEK chose to merge Imago with a business unit called CAMECA, which is headquartered in Paris, France, and they have actually their own interesting history. They started in the 1920s as a movie projector company, and they really developed this optical and projection technology together with scientific instrumentation for many years. And including one of those products called the Scopatone, which was the forerunner to MTV, which funded a lot of the development of scientific instrumentation in the 60s and 70s. And 2014 was a good year for me because I joined the team at CAMECA. So today, we are headquartered, the Atom Probe Technology Center is headquartered in Fitchburg. We have 78 employees, and about a quarter of those are UW-Madison grads. We have about 150 systems worldwide, Europe, North America, and Asia. So pretty much an even split between Europe and North America, with a larger fraction in Asia. And most of our customers are academic labs, so universities, academic institutes, but we have quite a large fraction of this pie, 24%, which are large semiconductor manufacturers. So these are the folks who make your phone, who make the chips in this laptop. And I think this slice of the pie really proves that Tom Kelly was correct. Unfortunately, there's no way that the largest semiconductor companies in the world are going to buy technology put together by a grad student in an academic lab. And I know because I was a grad student, right? So, you know, these are solving problems that are really relevant to all of us today. Okay, so now that we've gone through a little history, I'd like to talk about something that's very near and dear to my heart, which is applications, and particularly how we can determine the age of the Earth using the atom probe. So it's pretty well accepted that the Earth is about 4.5 billion years old, so 4.5 giga-annum. And about 50 years ago, the prevailing view was that the Earth had these molten magma oceans for quite a long time, so from 4.4 billion to about 4 billion years ago. Now, I think a lot of folks felt like it wasn't realistic to maintain this molten surface for so long, but until you can find a rock that is, 4.4 billion years old, you don't really have a lot of evidence against that. And this idea of when the Earth was cool and able to form solid rocks is kind of important, because if the Earth is cool enough to form solid rocks, then shortly thereafter, it's cool enough to form liquid water, support liquid water. And if it can support liquid water, then life can start to form here on Earth. So to determine the age of the Earth, we use these special rocks called zircons. Now, these are special because they have elements that decay at very well understood half-lives. So for example, the isotope 238 of uranium decays to lead-206, uranium-235 decays to lead-207, and thorium-232 decays to lead-208. Now we can measure, the distribution of these different isotopes of lead, and if they all agree and are pointing back to the same number of age, that is a measurement that is said to be concordant, and it gives really strong evidence that the rock is a particular age. So again, our story takes us into Wisconsin, right here in the geology department at UW-Madison with Professor John Valley. Now he was using a technique called secondary ion mass spec, it's related, and he had used that isotopic analysis to date this particular piece of rock to 4.4 billion years old. So you'll notice here that we have this blue center of the rock as well as a gray sort of rim. Now that rim was formed by a known geological heating event at 3.4 billion years ago. So 1 billion years after the blue part formed, the gray rim formed. Now, one thing that always hangs over the head of these type of measurements is the issue of lead mobility. So remember, we're measuring these isotopes of lead. And if lead can diffuse in or out of the crystal, then we have a problem because that's going to bias your measurement. So this type of isotopic dating definitely assumes that this is a closed system in terms of lead isotopes. So here's what the atom probe data looks like from that particular rock. Now we noticed something interesting with the atom probe data, and that's the presence of a large number of clusters. So these clusters have yttrium as one of their primary components, but also a lot of evidence of lead-206 and 207. And what this data set essentially gave us was 3 isotopic clocks in one data set. We can look at the overall measurement of all the lead and compare that to our concordance curves, and that really supported the SIMS measurement of this rock being 4.4 billion years old. So that's great. Now, we could look at the clusters separately from the rest of the data set, and that gave us an age of 1 billion years, so around the time of the heating event. So what had happened was all the lead that had decayed in that crystal had enough energy to get pushed together into clusters and locked there. And then we can look at the matrix separately from the rest of the data set, and that gave us an age of 3.4 billion years, so from the heating event to the present. Now this atom probe data also showed us something interesting because these clusters were only about 10 nanometers apart. So that heating event that gave this rock a lot of energy was really only enough to move that lead a few nanometers rather than a few microns through the crystal. So we really kind of settled that question of lead mobility because it didn't have enough energy to be moving microns in or out of the crystal. That also supported the SIMS measurement that the rock was as old as we thought it was. So not only can we apply this technology to rocks here on Earth, but we can also apply it to rocks found on the moon, which has zircons. So Dr. Jenica Greer, one of our customers, used this technique at Northwestern University to date the moon to 40 million years older than originally thought. So I think that's out of this world. So I want to talk a bit about a few applications that we're seeing in the lab and how they might affect your own lives. The atom probe can be used to look at things like bone implants. So how implants for medical devices, how the ion diffusion from those implants gets formed into newly formed bone tissue. Now, thankfully, they're testing this on sheep rather than people at this point in time, but still good science. We can look at things like nuclear materials, so structural materials used in nuclear reactors, and how this irradiation may make them more brittle over time. We can look at other geological problems, how earthquakes happen where they do, and of course, how old is the Earth. We can look at how precipitates of particular metals help to make your steel stronger, especially at high temperatures. So landing gear of airplanes, for example. And we can look at battery materials, how those might be affected by repeated cycling and charging and discharging. But if I look ahead into where we might be going with this technique, I'm reminded of a lecture given by Professor Richard Feynman in the 1950s. And the title of this lecture was "There's Plenty of Room at the Bottom." He wasn't talking about his physics students' career prospects. He was talking about this idea of nanotechnology. And if we can manipulate atoms, individually, this could be a really powerful idea and technique, because we can make, nanobots to do work or calculations for us. Now, I would say that over the years, I've really found this to be actually already the case. So this is a chart from the largest semiconductor manufacturer in the world, TSMC, and it shows the size of their transistors over time. Now, generally, they follow something called Moore's Law, where the number of transistors on a wafer doubles every 18 months. So currently, we are right down here between 5 and 3 nanometers. This is the size of the chips doing calculations in your phone. And this is what we're analyzing with the atom probe. So I would have to say I agree with Professor Feynman. There's plenty of room at the bottom. There's plenty of technology that's being developed at this size scale, and there's plenty of need for materials characterization techniques like the atom probe to be figuring out where those atoms are and figuring out what the problems are for those, let's call them nanobots. So I think after going through these applications, if you know someone or love someone with a hip implant, if you use a cell phone, that might be everyone here, I think a lot of these really embody the Wisconsin idea. And that is that the university and its research is meant to serve the people of Wisconsin. These material science problems touch all of our lives, and characterization is really needed to solve some of these problems and make life better for all of us. So with that, I'm actually really looking forward to getting to the Q&A, but I'd like to thank the Wisconsin Institute of Discovery for this amazing opportunity. There's plenty of folks at CAMECA, both past and present, who have really made this dream a reality, and really a wonderful place to work. So I found the biggest picture I could of everyone, which is still not enough folks. And special thanks to Dr. Tom Kelly, who's here tonight. Thank you, Tom, for all you've done. And of course, looking forward to hearing from all of you. So thank you so much for this opportunity. And yeah, thank you, Shelly. Should I keep this on or turn this?
Keep it on.
Okay.
Yeah. Thank you so much.
Yeah.
That was fascinating. All right, so we'll open this up for some questions from the audience. Sam will come around with a microphone. If anyone has questions, I'll go ahead and start with the first question.
I'm looking forward to it.
And this question actually comes from a high school senior, my high school senior daughter, who's interested in nuclear engineering. And she was fascinated by the information I shared, but had more of a question about your journey as a female scientist.
Oh,
and
okay.
Kind of wanted to get kind of your perspective on your experience.
Yeah, that's a great question. I think in a lot of engineering disciplines, we're, used to being one of the only women in the classroom, and that can be tough. I was a chemical engineer, which tends to have a lot more ladies, because there's a lot of biological problems that generally people are more interested in, ladies are more interested in. So I would say that my PhD class was just about 50-50 at the University of Colorado, and then my postdoc. When I look at the 10 years I've spent at CAMECA, I can see that the number of women in studying material science problems is increasing. That gives me a lot of hope. But, there's always challenges that come with being, a minority of some sort.
Right. Thank you.
Yeah, thank you.
Any audience questions yet? I have a few more that I can. Oh, we've got one up here, Sam. Thank you. If you want to move.
Yeah, I just don't want to fall off. So right. No, thank you, Shelly.
Hello.
Hi.
My name's Emily. I'm a graduate student in the chemistry department, but I'm in a group that's in geoscience, so studying like geochemistry. And my office is actually.
I'm not a geoscientist.
Yeah. My office is actually like right next to John's, which is fun. So it's fun hearing you talk about his paper. But my question with the atom probe was, so you use the mass spec in order to differentiate between the different atoms.
Yep.
How are you measuring the 3D position space data?
So, our detector is going to tell us where those ions essentially hit. And we apply a model that we can basically back calculate where they came from. So during the reconstruction process, there's some assumptions made from that, taking that raw position data and creating a 3D reconstruction. So the Z position comes from the order that they hit on the detector. So the early ions are at the top of the data set and the later ions at the bottom of the data set. And then that 3D position is applied during the reconstruction process, which is done in software.
Okay, that makes sense. Thank you.
Yeah.
Any other audience questions? I have another student question.
Please.
So the question was, are there any external factors that affect the functionality of the probe, such as altitude?
Altitude, wow. Well, we do have a customer in the middle of the Austrian Alps, and I think they're still getting really good data. But generally, the atom probe is conducted at cryogenic temperatures, so temperatures that are colder than the dark side of the moon and under extremely high vacuum. As you're evaporating ions one at a time, you really don't want any gases that can disrupt the flight path, I'll say. So I would say that this is done in a very controlled environment. You want to keep this high-tech machinery in a room that's somewhat climate controlled. I'm aware of one that began to rust from the inside. I think it was in India because it just wasn't air conditioned. But I would say that from the data itself, it's in a pretty carefully controlled environment.
Okay, thank you. Any audience questions yet? Okay, I got another one for you.
All right.
So I know you said squishy and biological samples are bad.
Mm-hmm.
Are there any other types of materials or certain elements that are easier or harder to work with than others?
Well, yes. So a lot of our primary applications from the old days were metallurgy. These things tend to evaporate really well and really well ordered. So there's a lot of big problems in metallurgy that can be solved by the atom probe. Now, in terms of things that don't work as well, interfaces that are weak. So as you're evaporating things one at a time, it puts a lot of stress on your sample. And these things can crumble or fly apart if they can't hold together during this very, energetic process. So materials that maybe aren't biological but are kind of softer or not that conductive or have pores in them, I think these, generally don't yield larger data sets. Now, metal, sometimes you can run them for several days. So just depends.
Okay, thank you. Any audience questions? There we go. Oh, got a couple.
Okay, so let's go back to the sheep.
Okay, let's go back to the sheep.
So we put an implant in the sheep,
Mm-hmm.
and you're looking at migration of ions from the implant into the sheep bone into the
Yep.
sheep.
So what they were doing, this was done at the University of Sydney, and I was told that only 22 sheep were harvested for this study, which to me felt like a small flock, but so what they were doing was looking at the ions from that implant and how they were formed, how they were incorporated in newly formed bone tissue. So bone tissue is alive. And we just talked about how we can't really analyze a lot of squishy things. But what you can do is freeze this bone tissue and use this electron microscope fib to prepare your sample when it's frozen. And these are methods that are kind of new, but kind of exciting. And that's what they used to get this sample, even though it was a biological material, into the atom probe and figure out that ions from the implant were being incorporated into that newly grown bone tissue. Well, I don't know if it's making it stronger or weaker, but maybe you don't want some of these things to be incorporated into your bone, right? I think they were looking at aluminum ions in particular. So, it's the importance of having, non-toxic materials as well to do these. Now, there was some other work with bone looking at the interface between bone and titanium hip implants. And you can see that this is forming kind of an interfacial region where these are really growing together. So I don't know if it's good or bad. I'm not a biologist or a real doctor, but this is the things that you can find with the atom probe.
So Katie, I wanted to know what the first material was that you did atom probe on, and why you got excited about that.
Oh God, it's taking me back. It was kind of interesting because I was maybe not qualified for the job when I got hired, but you can learn, right? And so I didn't approach, starting to work at CAMECA from somebody who had already done atom probe. And, it makes sense if you join a company that makes this, they have the experts there that can teach you this stuff. So I was in, related material science fields. The first material, I remember working with my colleague, Dr. Yiming Chen, and looking at some steels. And we were comparing these different microscopes, and I think that was a really exciting time for me because we were getting a lot of data on steels. Now, maybe steel isn't that exciting to everybody, but it was to me.
I was just curious if there's ever any collaboration with other area companies like Phoenix, where they do the neutron imaging, because some of what problems you're trying to solve seem like some of what they're trying to solve.
I don't recall any collaborations with Phoenix specifically, but we certainly do have a lot of collaborations with the University of Wisconsin. And, it's been great to work in a company that is so close to a wonderful university like the UW, because there's, so many interesting problems like John Valley's work, or a lot of the other types of microscopy techniques like transmission electron microscopy. And a lot of the computational work is also done right here, like machine learning. So I don't recall other companies per se, but certainly the university quite a bit.
Yeah, I was just thinking there could be situations where you have the destructive way of looking at a material, and then they're looking at a finished product and just looking at the image.
With our demo process, we take materials, we analyze them, we write a report, and send it to the customer so they can apply for funding, essentially, or get some justification. Now, it's kind of unusual for us to get the feedback about what part they're using or what's important about that. So a lot of times we're getting this data, we're throwing it over the fence, and we don't really see how cool or how important it is. So I totally agree. It would be great to have the entire feedback loop of what's the other data that's showing this is good or bad or whatever. We'll analyze one sample, get this data, analyze this sample, get this data, and never know what happens to it. So I wish we did that more.
Thank you. Another student question.
Yeah, please.
When organizations or institutions get one of your atom probes, what kind of training or education is involved for those groups?
Well, usually someone from our team would go there for about a week and spend that time with them, training them on how to use that. We also have a variety of online training materials. I would say that one of my favorite parts of the job is customer training, because you really get to spend time with people, and it's very rewarding to teach someone how to use an atom probe and see the delight on their faces in getting data on their samples.
Great, thank you. Any other audience questions?
I think we have one in the back.
Yep.
Why are you studying on sheep?
Well, sheep can tell us a lot about the human body. We can test things in sheep that are relevant to humans. So we can look at how, you know, implants that make your knee better or worse can affect the human body by testing it first on sheep. That's a very good question.
Favorite and least favorite parts of your job?
Favorite and least favorite parts.
Am I gonna get fired? My favorite part is working with my coworkers. They are some of the many of them are here tonight. But no, in reality, we work with really some very motivated and very intelligent people, and we have all gotten along really well. And I think the evidence of that is how long people have stayed at CAMECA. So you ask people, it's 20 years, it's 10 years for me, 15 years for somebody else. It's not a company where people really change jobs too much. So I think that, you know, gives a lot of evidence to people really liking their jobs. Least favorite part of the job. Dealing with vendors, like our service vendors, I don't know.
Thank you. Any other audience questions? No? Okay, so I had one other question for
Lay it
you.
on me, Shelly.
All right, so looking ahead 10, 20 years, what excites you the most about this technology, or where do you hope to see it going in the future?
Well, one problem that we've been working on a lot recently is semiconductors. And I think I showed that a little bit at the end, where these transistors keep getting smaller and smaller. And I think a lot of us don't really appreciate how much technology goes into the phones and cameras that we use every day, connecting to the internet, for example. And I think that this is also not really visible in society because the semiconductor companies are extremely secretive. You know, if they bring something to our lab, it might be something that the other guys made, you know, because they can't let that technology out of their lab. So I think, you know, when we see these problems that people are working on, you know, they're very important problems to all of our lives and just aren't really talked about in society. So I am personally excited about semiconductors. I want to work in that area with the atom probe more and more, and I think that's where we're going.
Great, thank you. And thinking about education and students and seeing workforce come in and students either doing internships or working, what do you think is the most valuable thing students can be doing at the undergraduate, graduate level to prepare themselves to work in a field like this?
Yeah, that's a great question. You know, one thing I think is really important is communication skills. And, you know, you can be a great scientist, but if you're not communicating your results effectively, then you're not going to be a good scientist, really. So I think that working on listening, reading, writing, that really helps out a lot. And one thing that I really helped me out as a graduate student was this quote that 6 months in the lab is going to save you an hour in the library. So reading and figuring out what other people have done is going to avoid you repeating this work, and a lot of times it'll give you really valuable insights that can help your research.
Great, thank you. Are there any other audience questions?
I really appreciated all of you being here tonight. Thank you. And thank you for the great questions.
Yeah. Thank you so much, Dr. Rice, for being with us tonight and providing your perspectives on the LEAP technology. Our next Crossroads of Ideas will take place on Wednesday, March 13th in partnership with the UW-Madison Communications, and will feature the topic of science communication and paleontology. More information can be found on the Illuminating Discovery Hub website. Thank you all for being with us tonight, and have a great rest of your LEAP Day. Thank you.
Great question, Shelly.
My daughter will be.
Yeah. Tell her she really came through.
I will.